Hi everyone, today we're going to go through reaction kinetics MCQ. Let's start on the first question, ACJC Prelim 2018. Right, the reaction of nitrogen monoxide and hydrogen gas is as shown, is thought to involve the following steps. Which of the following about the reaction is true? Hydrogen acts as a catalyst. I don't think hydrogen acts as a catalyst in this question because actually hydrogen, you can see that it is being used up but it's not being regenerated, right? So it's actually more like a reactant. Okay, so this is out. The rate of reaction for the rate equation for the reaction is rate equals to K N2O2 H2. You can actually see from the slow step, right? You can see from the slow step, rate equation is obtained from the slow step, which means this. I can write down the rate equation to be rate equals to K N2O2, right? This one because it's 1, so to the power of 1, right? The first order. Here so 1, so first order also respect to hydrogen. Can you see that? First order respect hydrogen, first order respect N2O2. But the problem is N2O2 here, you can see that N2O2 is a catalyst. Not a catalyst, it's an intermediate. Okay, it's intermediate. So because it's an intermediate, it cannot appear in your rate equation. It is being produced and then after that is being used up. So it's an intermediate. It cannot appear in your rate equation. So you have to replace it. So how do you replace it? You replace N2O2 by replace it with 2NO. Alright, so actually there's a bit of I'm just going to show you the proof. So if you look at step 1, right, it looks like that. Kc equals to concentration N2O2 over NO squared, right? So you can see from here N2O2, the concentration is actually Kc NO squared. So you take this and you sub in here. Alright, so this will look like that. Kc NO square H2, right? So NO is fine because NO is a reactant. So actually, in fact, I would say it's K prime NO square H2. Okay, so which means it follows this rate equation. So B is definitely correct. Okay, so the answer should be B. The overall order is so you look at it, this is definitely wrong because this is over here you can see is second order, but this is only first order, right? So this definitely this is wrong. Okay, the overall order is 3, yes. Okay, so 2 plus 1 equals to 3. As you can see, it's actually going to be a third order reaction. Okay, so definitely this is C. Increasing the concentration NO does not change the rate of reaction. It's not true because if I increase NO over here, the rate will definitely increase. Okay, let's look at question number 2. Alright, hydrogen peroxide reacts with acidified iodide liberating iodine according to the reaction. And they gave you these two graphs and they asked which of the following shows the correct labeling of the x-axis. Okay, so this is the rate equation. Rate equals to K H2O2 I minus. Can you see that? Okay, so for graph A, you can see that it's plotted rate versus x and it's proportional, right? So because of that, I'm thinking that x should be this entire part, right? So it's almost like rate equals to kx. So you plot a graph of rate versus x, right? You get a straight line sloping upwards, right? So the first the one I'm going to pick will be A or C. Okay, for the next one, over time, y is actually decreasing. Okay, y is actually decreasing. And you can see that for this kind of graph, okay, if you remember, for this kind of graph, sloping downwards kind of graph, all right, it's actually what I call zero order with respect to A, right? So which means that no matter how the A concentration changes, right, you realize that the rate never change, right? The rate doesn't stay, the rate stays the same, right? The rate is actually the gradient. So what is zero order? You can see that it's first order respect to H2O2 and I minus, and you see over here there's H plus as a reactant, but it's not found in the rate equation. So in fact this should be zero order because it's not seen in the rate equation. So definitely I should pick A. Alright, so this answer should be A. Okay, let's look at the next question. Okay, a very similar question, right? So we just look at the table and let's try to do it. Okay, number 1, which of the following statements are correct? So if I compare, maybe we should find the order of reaction first. So I'm compare experiment. Now let's compare. Okay, let's compare. Okay, let's give a minute. Okay, let's compare, say, experiment 1 and 2. Okay, I'm going to label 1, 2, 3, 4. Compare experiment 1 and 2. Alright, so keeping this the same and the same, this one triple. Alright, you can see that the rate actually triple. So compare experiment 1 and 2 is actually first order respect to H2O2. Okay, first order respect to H2O2. Remember it again. First order with respect to H2O2. Okay, so let's look at the next one. Okay, let's compare experiment 2 and 3. Okay, keeping this the same. When I double this, what happens to the rate? Okay, the rate also doubles, right? So I say compare experiment 2 and 3. It's gonna be first order. All right, first order respect to I minus. Again, because the rate the I minus concentration double, the rate also doubles. Okay, let's look at the next one. Okay, now we shall compare experiment 3 and 4. Okay, experiment 3 and 4. So keeping this the same, and I double this, you notice the rate doesn't change. So it's actually 0 order. All right, 0 order respect to H plus. Okay, so let's see. So I can actually write the rate equation already. So rate equals to K H2O2 I minus. Is okay? So this is definitely correct. 1 is surely correct. The reaction is second order with H plus. Nope. In fact, it's 0 order. The value of the rate constant is 0.2. So what we can do is we can actually sub in the value. Right? So I'm going to use just experiment 1. 2 times 10 to the power minus 6. I'm going to use experiment 1 equals to K. Concentration of H2O2 and I minus is actually 10 to the power minus 2. 10 to the power minus 2, right? Okay, so you can see that K will turn out to be 2 times 10 to the power minus 2, right? Which is actually 0.02. Can you see that? So this is definitely wrong. So answer will be A. Okay, let's move on to question 4. Alkaline hydrolysis of 2-chloro-2-methylpropane with 0.2 mole per dm³ of sodium hydroxide produces the product here. Okay, they say 20% of this tertiary halogen alkane of concentration hydrolyzes in 5 minutes at a certain temperature. With reference to the overall order of this reaction, what percentage in a solution of concentration 0.04 will also hydrolyze in 5 minutes? Okay, so the thing is this, all right? So it's almost like half-life. The concept is almost like half-life. So you notice if something like for a concentration of reactant, say for example it starts from 1. All right, this is the graph. Okay, this is the first order with respect to A, right? So if it drops by 50%, all right, means 0.5 drops by, over here, this is a decrease by 50%. So the time taken is the half-life. This is a half-life, okay? And after that, for 0.5, it drops by another, here, it drops by another 50%, right? And the time taken would be the same. This will also be half-life, and they are the same. So for first order reaction, what I want you to learn is this. When the percentage drop is the same, the time taken would also be the same, right? So the time taken will be the same if the percentage drop is the same. So it doesn't have to be just 50%, all right? If it drops, if it takes, say for example in this case, if it takes 5 minutes to drop by 20%, so the next 5 minutes, it will still drop by 20%. Are you me? So as long as the time taken, all right, is the same, all right, the percentage drop would also be the same. So in this question, in fact, it is also 20%, because the time taken is the same, so the percentage drop is the same. The percentage drop is the same, but the absolute concentration drop, of course, will be different. Like you can see from here, drop by 0.5, but this only dropped by 0.25. Okay, so that's a learning point. Okay, let's look at the next question. Question 5. Okay, let's see from this question. This is I'm going to write the rate equation again. Rate equals to K O2 NO squared. All right. So so we already know that is first order respect to O2 and second order respect to NO. Okay, so let's try to do the first one. Okay, I'm going to call this 1, 2, 3, 4. All right. So looking at experiment 1 and 2, when I halve this, keeping this the same, O2 is first order, right? So if I halve the concentrated O2, I believe the rate would also halve because it's first order. So S will be equals to 4. Okay, so I'm just going to put A and B. Okay, now since I already know it is 4, I can actually continue. I put 4 here. So we'll put 4 over here. All right, 4.0. Okay, now I'm going to look at experiment 2 and 3. All right, 2 and 3, keeping this the same. Okay, from here to here, you notice is multiplied by 4. All right, and for NO is actually second order. So in fact, if the rate increased by 4 times, actually what it means that the concentration actually increased by 2 times. All right, that's why the rate square it. The rate here 4 is because it's 2 squared. Can you see that? So it's the second order. Right, so which means T must be equals to 2. Right, so this is done. Okay, maybe you just finish up the last one. We know the answer is B already. So but maybe we just try to do the last one. Okay, maybe I just put T as 2. All right, never mind, it's fine. Okay, so from here to here, all right, I half it. Can you see that? I half it. From here to here, in fact, what's happening is I multiply by 1/4. Okay, I multiply by 1/4. So in fact, when you halve the concentration of O2, the rate will halve. When you 1/4 the concentration NO, all right, the rate will actually decrease by 1/4 squared. Can you see that? So which means from here to here, I must multiply by half and then multiply by 1/4 squared. Okay, and you can easily see that U will be 0.5. Okay, so that's why anyway this is the answer. Okay, all right, okay, let's do a question 6. Okay, so what are reactants? The reactants are H2O2, H plus and I minus. And if you look at the slow step you notice involves H plus. All right, the slow step involves H plus means H plus must be part of your rate equation. But since I don't see any H plus over here, this is actually not correct. Okay, so because it should be at least first order respect to H plus, but I don't see any H plus here, so I know this rate equation is not consistent. All right, okay, if I look at this question here, okay, this is the equation, right? And then you see the rate equation and you see that. So if I'm looking at it carefully, rate equals to K, slow step, right? So there are 2 NO, I'm going to write NO 2 squared. Okay, so it's actually based on the proposed mechanism and the rate equation is correct. But if you look a bit deeper, you realize that when I add these two equations together, what do I get? You notice I can cancel these two. So if I add these two equations together, this is my equation. Okay, this is my equation. All right, and 2NO 2 plus CO to give you O plus CO2 plus 2NO, right? So it looks kind of strange because it doesn't fit. Okay, it doesn't fit. All right, so that's why this one is definitely out. Okay, even the proposed mechanism, we add them together, it doesn't give you the overall. So there's something wrong with it. All right. Okay, let's look at the third one. Okay, third one, this is a slow step. So rate equals to K H2 to the power 1. All right. So but you can see there's I2, so this is also out. So that's why the answer is none. Okay, let's move on to question 7. Okay, let's do question 7. So wow, this reaction seems to be kind of popular. We've been doing a few already. Okay, which of the following conclusion can be drawn from this information based on the proposed mechanism? The acid is acting as a catalyst, right? So you can see from here, H plus is used up, but it's not being regenerated, so this is out. The reaction is pseudo first order respect to H2O2. So if you can see from here, the rate equation is actually K H2O2 I minus, right? So H2O2 is actually a reactant. So they say pseudo first order respect to H2O2. No, it's just a first order. Okay, first order respect to H2O2, not pseudo first order. Okay, so I'm going to cross this out. Okay, the reaction rate is independent of the pH of the solution. So this statement is correct. Okay, why is it correct? Because it's H plus here, but it's actually is zero order respect to H plus. So in fact, H plus doesn't affect the rate. So it's independent of the pH. Right, so this is definitely correct. So the answer should be B. Okay, let's look at the next question, 8. A first order decomposition reaction is shown below. The half-life of the reaction was found to be 3.47. What is the time taken to reach 1/3 of its initial? So okay, there's a formula. So let C be the concentration of a reactant at time t. Alright, C naught be the initial, and then half to the power n, where n is the number of half-life. So actually they say what's the time taken for it to reach 1/3 of its initial concentration. So say for example the initial concentration is 1, alright, and then after that some time becomes 1/3. So half to the power n. Okay, so you actually do the math to calculate what's the half-life. Alright, so you have to take logarithm in fact. Okay, log 1/3 equals to n log half. Alright, so n is equals to log 1/3 over log half equals to 1.6. Alright, so you think 1.6 half-life. So the half-life of the reaction was found to be 3.47 seconds. So what's the time taken? So time taken is equals to 1.6 times 3.47. Alright, which is about 5.5 seconds. Alright, so that's why the answer is C. Okay, let's look at question 9. Okay, actually question 9, the table is the same as question 3 just now that we did. So the rate equation, I'm just going to write down the rate equation. Alright, it was the same as the table is exactly the same as question 3. So the rate equation is rate equals to K H2O2 I minus, right? Or first order with respect to these two. And in fact, it's actually zero order respect to H. So actually, you don't have to write that. I'm just going to write this down. Okay, so this is what it should look like. All right. So what can be deduced from these results? So the rate equation is correct. Okay. The reaction is zero order respect to acid, which is correct. The units of the rate constant is so much. Let's check it out because this is second order reaction. So the unit of K, right? Essentially, going to write down rate over concentration of H2O2, concentration of I minus. So if you're going to plug in the values, unit for rate is moles per dm cube per second, as you can see. All right, and then of course here is just moles dm cube per dm cube squared. All right, so in the end it should be moles minus 1 dm cube per second. All right, so actually this is wrong. Okay, this is actually more for a third order reaction. Okay, both hydrogen peroxide and iodide are involved in the rate determining step. Definitely, all right, because these two are found in your rate equation. Okay, so the answer will be 1, 2, and 4. Okay, let's look at question 10. Okay, so let's look at the rate equation. Rate is equals to, you have to look at the slow step, right? So the slow step involve R and Q, so it's first order respect to R and first order respect to Q. Okay, but if you look at it carefully, you realize that if you add all these equations together, the R can cancel out and the S will also cancel out, and in reality the reaction is actually 2P plus 2Q, all right, to give you P2Q2, right? So you realize that actually R is actually an intermediate, right? It's intermediate. So intermediate cannot be part of the rate equation. So because it cannot be part of the rate equation, you have to try to replace it. So you have to look at the fast step, and this R came from 2P. So you can actually replace this R with P squared. Okay, but of course the K is a different K, but just going to put a K prime, right? So this is what it should look like. So A is correct. Oh, A is done already. So actually the answer is A. Okay, the overall order of reaction is 2. No, it's in fact is 3. The units of the rate constant is this. So this actually is, we just did it. This is for a second order reaction, but this is actually a third order reaction. So this is also out. Okay, how about D? The half-life of Q is half when Q is double. Okay, when they say the half-life of Q, right? The thing is this. If you look at it carefully, okay, if you look at it carefully, maybe I just write the whole thing again. Okay, I just write it this way first. Okay, to have a half-life of Q, it must be a pseudo first order reaction, right? And that only happens when P is in excess, right? So I'm going to write down as K prime Q, right? So what's K prime? K prime equals to K P squared. You see that? So what's half-life? So half-life of Q is equals to ln 2 over K prime. Okay, this is the K prime, which is ln 2 over K times P squared. Can you see that? K times P squared. Replace the K prime by KP squared. So you realize that the half-life is affected by concentration of P, not concentration of Q. So when they say the half-life of Q is half when Q is double, this is definitely wrong, because half-life is only affected by P in this case. Alright, okay, so yeah, okay, so let's move on to the next question. Question 11. Okay, so all you need to do, all you need to remember is looking over here by the unit of the rate constant. The unit of rate constant will tell you it is actually a third order reaction. So maybe if just a quick summary, for a zero order reaction, for zero order, right, the unit of K is usually the same as the unit for rate. Okay, so for first order is just per second. For second order, it's actually moles minus 1 dm cubed per second. So third order, you realize it's actually moles minus 2 dm6 per second. Alright, so which means, looking at the unit over here, it's actually a third order reaction. So the answer has to be C. Alright, so learn this by heart. So at question 12, alright, so based on the first table, we shall find the order respect to P and Q. So you can see from here, when I'm going to compare experiment 2 and 3 here. So when I double this, the rate also doubles. So we know it's going to be first order respect to P. It's okay. So first order respect to P. Okay, let's do this again. All right. Okay. So how about Q? So I'm going to compare experiment 1 and 2. So you can see that I double over here. This one also double, and what happened? The rate also double. So when I double this, right, since it's first order, the rate will already double. Okay, and since the rate already, the overall rate already double, right, it means that doubling of this didn't affect the rate. Okay, doubling of the concentration of Q didn't affect the rate, so we must know that it's actually zero order respect to Q. All right, so I'm going to write down rate equation. Rate equals to K P. Alright, so this is the rate equation. Okay, so actually we don't really have to bother about Q anymore, because Q is zero order, it doesn't affect the rate. So we just have to look at P and the temperature. So they say the rate constant doubles for every rise in temperature. Alright, and then they ask you to compare the experiment 4 to 6. Okay, so let's look at experiment 4. So I say, for example, if I say experiment 4 is the reference point, the rate is X. Okay, I'm going to write down rate. The rate is actually X. Okay, let's look at experiment 5. So when I double this, I'll cause the rate to double because it's first order. And this one will, when I minus 10 degrees Celsius, right, it will cause the rate to what? To half. Okay, and this one will cause the rate to what? To double. It's okay. And hence you can see for experiment 5, the rate half here and then the rate double here, so the rate has no change. So I'm going to put an X over here for this one. Alright, so no change for the rate. Okay, for experiment 4 and 5. Okay, let's look at the last experiment, experiment 6. Over here, let me compare. Maybe I compare 4 and 6. 4 and 6. So from here, I'm going to multiply by 3 the concentration, and over here, in fact, it went down by 10. And then went up by 10 again. So this actually minus 20 degrees Celsius. I'll say that the weight row must multiply by half, okay, drop by half, and then drop by half again. Okay, so which means that the overall rate relative to experiment 4, okay, this is 1/4 and this is the weight row times 3, right? Because first order. So this is 1/4 times 3. Can you see that? So which means, I'm just going to take away this, which means 1/4 times 3, right, is 3/4, which means this is supposed to be 3/4 x. Okay, so now we can actually check the options. Rate of reaction experiment 4 and 5 are the same. That's true, okay, because both are x. The rate of experiment 4 is 2 times faster than that of experiment 6. Not true at all. Rate of experiment 6 is the slowest. Yep, it's actually the slowest, you can see, right? Yeah, so this is the slowest. So the answer be 1 and 3. Alright, okay, let's look at question 13. The half-life of first order gaseous reactant X2 molecule is converted to X. So it's going to write, you have to write it like that. Okay, 1 mole of X2 is placed on a sealed vessel at pressure P. Which of the following will be correct when 87.5% of X2 has been converted? So if 87.5% of X2 has been converted, it means there's actually 12.5% of X2 left. Alright, okay, so take it is this way. If I started with 100, okay, maybe if you think about it, right? You start 100%, drop to 50%, drop to 25%, and then you drop to 12.5%. So you can see that this part here is actually 3 half-life. Okay, 3 half-life. So if it's 3 half-life, it means that the time taken will be 60 minutes. Okay, each half-life is 20 minutes. So this is definitely correct. Okay, 1.75 moles of X atoms have been formed. So let's check, is it correct? So this is ICE, yeah? Okay, so initially 1, 0. In the end, since you have 12.5% left, right, we'll put 0.125 moles left, okay? Because you started with 1. So this one will be minus 0.875, this one plus, okay, so you must multiply by 2, so it's going to be 1.75, okay, because the ratio is 1:2, so you must multiply by 2. Okay, so in the end, 1.75 moles of X atom have been formed. That's correct. 1.75 moles of X atom has been formed. So this is definitely correct. Okay, I'll put a tick over here. Okay, the total pressure is 15 P over 8. Alright. Okay, so I'm just gonna change it to pressure. Okay, I'm going to change it to pressure. So it's actually the same thing, right? It's just they change it to pressure. So this is P, right? Sealed vessel P for 1 mole of X2, 0. So in the end, 0.125 P, alright, because 12.5% left, minus 0.875 P plus 1.75 P. So this is 1.75 P. So the total pressure, if you add them both up, right, add these two up, okay, you give you 1.875 P. Alright, and 1.875 P, if you press your calculator for this, you realize that this actually equals to 15 P over 8. Alright, so this statement is also correct. So it has to be 1, 2, and 3. Let's look at question 14. Thorium-234 undergoes radioactive active decay to form protactinium. Okay, so TH, right, becomes PA. Alright, so with half-life of 24.1 hours. So they say in the end, it contains a ratio of 2:3, molar ratio in the end. So you can see from here, actually this part here is actually 5 units. Can you see that? It's 5 units. Right, it contains 2:3 molar proportion, right? Then how many hours has the radioactivity taken place if the sample was initially protactinium free? Alright, so it means that actually here I'll take it as here is 5 units initially, alright, then change, and this is the final. So it's like -3 then +3. You can see that this is free of protactinium. Alright, okay, so so you can see that it started from 5 and then it ended at 2. So I'm going to use the formula CT original half to the power n, where n is the number half-life. So the final is 2, here is initial is 5, half to the power n. So I take logarithm 2 over 5 equals to n log. If I take log on both sides, it's okay. So n is equals to logarithm 2/5 divided by logarithm half. Alright, so you press your calculator, you should get a value of 1.32. Right, so this is the number of half-lives to reach to this value here. So what's the time taken? Time is equals to number of half-lives times the half-life, which is actually 24.1 hours. So this will give you a value about 33.9 hours. Okay, so the answer is going to be C. Alright, okay, so let's look at the next question, 15. If you look at they say which suggested mechanism is consistent with the experimentally determined rate equation. So this is a slow step. Alright, it involves 2 NO and 1 molecule of hydrogen. So this is what it should look like. Okay, second order respect NO and first order respect to H. So this is perfect. Okay, 1 is correct. Okay, this is a slow step. So rate equals to K N2O2 to the power 1. You can see from here. So you look over here, right? Okay, so to the power 1 and O2 to the power 1. Okay, but you realize that N2O2 is an intermediate. So you have to replace it. N2O2 must replace with NO square. Alright, so I'm just going to put K prime, but it'll be NO square. Replace this with NO square, because intermediate cannot be part of your rate equation. Alright, so this is what it should look like. So this is wrong, okay, because like what I said, N2O2 is intermediate, it should not be part of the rate equation. Last one, slow step, Cl and O3. So I'm going to write down Cl, KCl, and O3 over here. Okay, just for you to notice, in fact, Cl here, can you see it's actually used up and then is regenerated. So what is Cl actually? Cl here, Cl is actually a catalyst, right? And I want you to take note, a catalyst can actually appear in the rate equation. Okay, a catalyst can appear in the rate equation. Okay, so this is definitely correct. Okay, so answer is 1 and 3. So question 16. Okay, the decomposition of dinitrogen tetroxide is found to be first order respect to the concentration of N2O4, right? Okay, so I'm just going to write the rate equation. Just change it. Okay, rate equation is equals to K N2O4, right? So which of the following confirms above finding? So rate and concentration N2O4 is proportional. So this graph should look like that, not a straight line. Okay, look at B. So this is a first order reaction with respect to N2O4. The graph should look like this with a constant half-life. Okay, let's look at C. Okay, let's look at C. If you're going to write it in a different way, like this, N2O4 equals to K. So K is a constant. So this is actually correct because rate over this is equals to K, which is a constant. So the answer is going to be C. Right, but let's look why is it not D. D, what you need to do is you're going to take logarithm on both sides of this equation, right? So it looks like that. It's log K, log rate. It's going to be log rate equals to log K plus log N2O4. So I believe if that's the case, this is something like your y-intercept. You're plotting log rate versus this, okay? And this becomes the y-intercept. So which means I believe the graph should actually look something like this. Alright, it doesn't cut through the origin. Right, so this one is D is also wrong. So answer is C. Okay, let's look at question 17. Hydrolysis of the anti-cancer drug in water follows a first order kinetics, and this is the rate constant. Alright, how long will it take for the concentration to decrease to 18% of its original? So you must understand that this is the drug. Okay, maybe this is platinum. Okay, so you start with 100%, you're going to drop to 18%. Alright, so we're just going to use the formula CT equals to C naught half N. Alright, so in the end you left 18%, you started with 100%, half to the power n. So if I take logarithm on both sides after moving the 100 across, this becomes n log half. This, okay, if you do your mathematics, I think I've calculated already. So if you did your calculation properly, you should get a value of 2.47. Okay, you get a value of 2.47. All right. Okay. Now, and when they gave you this is actually your k. All right, the rate constant k. So with rate constant k, you can actually also find out the half-life. Can you see that? So this becomes ln 2 over 0.09. Okay, and you press your calculator, you get 7.7 hours. So this is your half-life. Okay, and this is the number of half-life. Okay, this n here is the number of half-life. So the time taken, it equals to the number of half-life times the duration of a half-life. Okay, so once you multiply, you get about 19 hours. All right, so the answer is going to be C. All right, so let's look at the next one, set 18. Okay, you are supposed to use the graphs to determine the order of reaction respect to the respective reactants. Okay, so one thing you need to take note is this. Maybe I just want to quickly explain. All right, if I give you A to become a product, and if you get a straight line down like that, you know this is zero order respect to A. If you get a nice curve with a constant half-life, you know it's actually first order respect to A. Okay, so since this is a straight line down, I already know it is zero order respect to X. And for Z, you can see there's nice half-life. So starting from 0.08, drop to 0.04, this is it. And then drop another half is here. So you can see that this is the half-life. Here to here is a half-life. Here to here is also a half-life, right? So the half-life is a constant, which means this, it must be first order. So with that, I can eliminate D. And with that, I can eliminate A. All right, so you still have to find out about Y. Okay, so let's check how to find out Y. Right, so in order to find the order with respect to Y, we look at the first graph. Y is 0.1 and now Y is 0.2. So when I double the concentration of Y, what happened to the rate? You move down 1 unit, go across. All right, for the other one, you move up 1, 2, 3, 4 units, and then you go across. So in fact, the gradient is actually multiplied by 4. Okay, so what I'm trying to show you is this actually. The blue line here, I think is 1 unit. And the red line here is actually like 4 units. You see that? Yeah. So it's actually 4 times. The gradient actually increased by 4 times, which means the rate also increased by 4 times. Right? So it means it must be second order for Y. Y, it should be second order. Okay, I hope you can tell it's going to be second order. Alright. Okay, so that means it leaves me the answer to be C. Okay. Okay, let's try question 19. Okay, SO2 plus O2 to give you SO3 in the presence of a suitable catalyst. So based on your A level, alright, you need to know that for this suitable catalyst is actually NO2. And the reaction works this way. So NO2 will first react with SO2, alright, to form SO3 plus NO. So NO is an intermediate. NO is an intermediate, you continue to react with O2 to form back NO2. It's okay? So this is how the reaction takes place. So NO2, right, is a gas, right, and it is the same phase as SO2 and SO3. So NO2 is a homogeneous catalyst. That's correct. Okay, it involves, and this catalyzed reaction involves forming a stable intermediate. Yes, because it forms a intermediate over here. So this is correct. Number 3, both activation energies of the forward and backward are lowered. Okay, so let's check it out. All right, so at first this was the forward activation energy. All right, but now the forward activation energy in the catalyzed reaction is just a tiny bit. Can you see that? Okay, so it actually has been lowered. So for the backward activation energy was at first over here. All right, but now it has been lowered. Okay, so now it's been lowered, is now over here. Can you see that? So this statement is also correct. All right, in the presence of catalyst. So which means 1, the answer is 1, 2, and 3. Okay, let's look at the next question, question 20. Butane ions can be dehydrogenated to form trans. The enzyme fumarase speeds up the reaction. So fumarase is an enzyme. Alright, it's an enzyme and it's a catalyst. Since they say speed up reaction, means this guy must be a catalyst, isn't it? So what does a catalyst do? A catalyst always lowers the activation energy and provide an alternative pathway. So which means this reaction, this answer should be C, because I can see that they wrote down lowers the activation energy of the reaction. Okay, let's look at question 21. Nitrogen is the final product formed by radioactive decay of carbon. So carbon will become nitrogen. Can you see that? Okay, what would be the age of the substance originally nitrogen free when the age of the substance, so originally nitrogen free, in the end it became 2:5. Okay, so since you know that the unit is 1:1, one carbon will become 1 nitrogen, and so the number of units won't change. All right, so over here you can see there are 7 units over here. Right, so originally there must be 7 units of carbon and 0 units of nitrogen. So the final for carbon is 2, the initial is 7. So I'm going to use the formula again, where N is the number half-life and C is the concentration at the end. So this one put 2, initial concentration is 7. Alright, and then this is what it looks like. Okay, log 2/7 equals to N log half. Okay, you can do the math. I've done it. Okay, and the answer for this calculation would turn out to be 1.8. Is that 1.8? So there's 1.8 half-life. So since it already gave you the half-life, so you know the time taken. Okay, the time taken for it to reach from 7 to 2, right, will be 1.8, the number half-life, multiplied by the half-life. Okay, so it will be approximately 1.04 times 10 to the power of 4 years. Okay, work it out yourself. You see that this is the answer. All right. Okay, let's look at the next question, question 22. All right. Okay, a student investigates the kinetics of the reaction by using a spectrometer. So the spectrometer actually measures the concentration iodine by measuring the absorbance. So the absorbance actually tells you the concentration iodine. All right. So the time taken for the absorbance of the reaction to reach a fixed value is measured over a range of hydrogen peroxide concentration. So the table looks like that. You vary the concentration of H2O2. So you do this experiment a few times. All right, you vary the concentration of H2O2 and you measure the time. All right, and this time is the time taken for a fixed, this is important, a fixed value for the absorbance of the mixture to reach a fixed value. Okay, what it really means is you are actually finding the time taken for a fixed amount of iodine to be formed. A fixed amount of iodine to be formed. So the rate actually is supposed to be change in concentration iodine, which is a product, over change in time. So you're actually measuring the time taken for a fixed amount of iodine to be formed, which means I take the numerator here to be a constant. Alright, so now you can see the rate will be proportional to 1/t, right? So the numerator is constant, so it's just time dependent. So which means you need to have one more column that puts 1/t, and this is actually your, I would call it relative rate. Okay, but it's just still rate. So what you need to do is you're supposed to plot a graph of rate versus concentration of H2O2 in order to find the order of the reaction with respect to H2O2. So since the question says is first order, respect to H2O2 is first order, it looks like the answer will be this, because since rate equals to K, H2O2, so rate versus this is proportional rate, and concentration H2O2 is proportional, and this is rate. Okay, and yeah, it's proportional. Alright, so the answer is D. Okay, let's look at the next question. So hydrogen peroxide undergoes complete decomposition. It's actually this equation, H2O2 becoming 2 water and then O2. Alright, and you notice over here they mentioned that 96 cm cube for a complete decomposition, 96 cm3 oxygen was produced. So it should look like that. Okay, this is 96, so it's volume O2 time. Okay, so they say it was found that 48 cm3 oxygen was collected in 35 minutes. So actually you notice, actually 48 cm3 is the halfway mark, right? Notice it's the halfway mark. 0 to 48 and 48 to this, from here to here, from 0 is 48 cm3 evolved. From here is another 48 cm3 that will be evolved. So 48 is the halfway mark. It also really means that half of the H2O2 have already reacted. So if you have that in mind, you'll realize that 35 minutes is actually your half-life. Okay, it's your half-life. Okay, I'm going to teach you this formula. You need to know this formula. Vn minus Vt is proportional to concentration of a reactant. So what's Vn? Vn is the final, okay, it's the final volume. All right, Vt is the volume at any point in time. All right, so let's try when time equals to 0, and this is the T1 is where you collect 80 cm3. So this one, when t equals to 0, okay, Vn first. Vn we already know is actually 96 cm3. Okay, so at time equals to 0, all right, at time equals 0, no gas evolved, so Vn minus Vt is equals to 96 minus 0, because no gas evolved here, which is 96. Okay, so this is the initial. All right, so this is when 80 cm3 gas evolve. All right, I call it T prime. Okay, which is this is what you want to find out, right? How long? Okay, so Vn minus Vt is equals to 96 minus 80 cm3. Okay, 80 cm3, which is so this will be 16. So what did we just learn? Vn minus Vt is actually proportional concentration of reactant. We can just take as if, we can treat it as if the reactant dropped from 96 to 16. So we're going to use the formula Ct equals C naught half to the power n. So if that is the case, Ct is 16, that's the amount of gas left. Initially is 96, right? Half to the power n. Okay, then you take log on both sides. Log 16 over 96 equals to n log half. All right, so you work it out. In fact, n will turn out to have a value of 2.58. All right, so this is the number of half-life. All right, half-life. So each half-life we know is 35 minutes. So the time taken for 80 cm3 of gas to be evolved must be 2.58 multiplied by 35. Okay, and that will give you a value about 90.47, right, which I'm going to put it as B as the answer. All right, okay, let's look at the next question. Question 24. Okay, they say if 10% of hydrogen peroxide in a solution of concentration 0.1 mole per dm cube decomposes in 5 minutes, what is the concentration of 1 mole per dm cube of hydrogen peroxide after 5 minutes? So if the time is the same, the percentage drop will also be the same. All right, so since 10%, they was mentioned at 5 minutes it will drop 10%, so the next 5 minutes you drop by 10%. So if you started with 1 and then you drop 10% after 5 minutes, you'll be left with 0.9. Okay, so that's the answer. Right, so it's okay. So as long as the time is the same for first order reaction, right, it must be first order reaction, of course. So if the percentage drop will always be the same. Okay. All right, so let's look at the next one, 25. All right, so NO plus Cl2 give you NOCl, and NOCl they say is a yellow gas. All right. Okay, so they gave you two graphs. One is color intensity of the gas mixture versus time. Okay, but how do you interpret a graph like that? Okay, so one thing you need to know is this. All right, so you have to go back and revise a bit of your kinetics. If this is the product time graph, what you'll realize if you have a reactant A to a product, okay, firstly what you need to find out is the final value of the final amount or volume of the product. So this is the first thing, maybe I call it C naught lah, okay? Yeah. So if the graph has this pattern, 0 to half, this is a time taken, T1, and from half C naught becomes 3/4 C naught, okay? This value here, all right? And if from half C naught to 3/4 C naught, I call this T2. So if T1 is equals to T2, in fact, T1 equals T2, right? It's a constant. In fact, T1 is actually a half-life. All right, this is your half-life. So if half-life is a constant, you can see that it implies, what it implies is it's actually first order with respect to the limiting reactant, which is A in this case. All right, so in this question, since they say this excess NO, so the limiting one is chlorine. Okay, the limiting one is chlorine, and you can see the time taken is T over here for the halfway mark, and then they say 3/4 of the maximum, right? 3/4 of the maximum is actually 2T. All right, so yeah, so you can see that the time taken to move from here to here, okay, from here to here, the time taken, and from here to here is the same. Right, so it means there's a constant half-life is first order. So this graph tells you it's first order with respect to the limiting one, which is chlorine. It's okay, so it's a constant half-life, first order with respect to chlorine. Okay, this one you can see that rate versus NO square is proportional. So if we know that this is second order respect to NO, second order. So this is going to be the rate equation, KCl2 NO square. Okay, NO squared. All right, so this is the rate equation. Okay, so first part, the reaction is first order respect to chlorine. That's right. A possible mechanism for the reaction is as follows. So we can imagine. All right, so if I wait, firstly I'll do this. I'm going to add up both of them, and I can see that it will give me 2NO plus Cl2. Yeah, it still does give me the overall equation. All right, so is this a possible mechanism? Okay, is this a possible mechanism? Let's think. Actually, it is possible. All right, why is that so? I'm just going to show it to you. So actually, we take the second step to be the slow step and the first step to be the fast step. So if this is a slow step, I'm going to write down as rate equals to K NOCl2 NO. All right, and you notice that this one is an intermediate. All right, it's not a part. It's an intermediate. So what you need to do is you have to replace it with one of this and one of this. So now if I replace it with Cl2, one of it, and one NO becomes NO square, including this, right? So this is what the rate equation should look like. Can you see that? So it's the same as the overall. So it's actually possible, provided the second step is the slow step. All right, so I'm going to put a tick here. This is fine. Okay, the rate constant has this unit. Okay, if you notice, what's the unit of the rate constant? Okay, what's the unit of the rate constant? So since it's a third order reaction, right? So I go right now, unit of K. Okay, it's a third order reaction. Rate over concentration Cl2 NO square. So this is actually moles per dm cube per minute. Can you see that? Over moles per dm cube. So you work it out, it's going to be moles minus 2 dm6 per minute. So I think this school question was a bit tricky. It's actually moles minus 2, but over here they put moles square, right? So this is definitely out. Okay, so the answer will be B, 1 and 2.
Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.